Started. We should be good to go. Okay. So thanks for joining me, guys. I appreciate you guys using your lunchtime here or your early afternoon post-lunch to join us today. I'm talking a little bit about wireless, specifically Wi-Fi and how it works. So I'm taking something here that's really technical, can get really complex, and I'm trying my best here to try to distill it down into some basic things to help you understand how it's going to work. I'm getting complaints here about my sound being choppy. Okay, let me see what we can do about that. I'm gonna try switching my headset. Give me just a second. Testing 1 2 1 2. Okay, Joseph, is my sound any better? Okay, we'll try this one more time. If you guys can hear me, go ahead and raise your hand in the Zoom interface. Okay. Unfortunately, this is as good as it's going to get on the sound. So if there's still having issues, I don't know what the cause of the problem is. So apologies, guys, and thank you everyone for raising your hand. So we'll go ahead and get started. Just real quick, for those of you that might be new Zyxel resellers and aren't that familiar with us, just one single slide here talking a little bit about. This is odd. Sorry, I'm getting weird pop-up errors now. So anyways, we've been doing this for about 30 years. We've been making computer networking equipment. We started off back in the early days of dial-up bulletin board systems and dial-up ISPs. We've got a little over 100 million devices deployed out in the field. Our US headquarters is based here out of Anaheim, California. So that's our sales, that is our warehouse, and that is also where our tech support is done. So if you call in and need some help, you are talking to someone who works at Zyxel, although these days they're working from home, not from our office. So we don't outsource it to third parties. We don't outsource it overseas. When you call in, you're talking to us. And our headquarters is based out of Taiwan. So that's where our engineering teams are at. That's where our R&D is at. So that's it for just a little quick summary of who we are. Now on to the today's presentation. So I want to talk here about a couple different names. So you'll see these out here, IEEE. It's an engineering group. They create different work groups that create the standards that make networking work. So whether we're talking Wi-Fi or wired, if you pull up the data sheet on any one of our products or one of our competitors' products, you'll probably see a whole list of IEEE standards that that product meets. When it comes to Wi-Fi, we're talking about 802.11. So you'll see 802.11a, 802.11b, R, K, bunch of other stuff like that. There's the Wi-Fi Alliance, which is sort of a marketing group. So their primary purpose has been marketing Wi-Fi and assuring compatibility between different vendors. So one of the problems, especially in the early days of Wi-Fi, was that the IEEE group spends literally years coming together with these standards, but still at the end of the day, they don't have any enforcement mechanism, and some stuff, excuse me, some stuff, is still open for interpretation of how you actually implement it. So the Wi-Fi group comes together and they created some testing criteria that everyone needs to pass in order to get the Wi-Fi certified logo. And it's primarily focused on interoperability between the different companies, different chipsets that are out there. And then we have the FCC, so that's the US federal government. These set the rules as far as what frequencies we can use, what sort of power we can use, and other things like that that come down to the technical specs. So those three groups you're going to see out there, it's the Wi-Fi Alliance that is rebranded Wi-Fi 802.11ax as Wi-Fi 6 and retroactively named 802.11ac as Wi-Fi 5, 11n as Wi-Fi 4, etc. And there we go. So Wi-Fi works using radio waves. Same things you use in your car to listen to music. The same things you use on walkie-talkies, especially those old walkie-talkies. If you grew up in a kid, the old cheap analog ones. And you'll see me using walkie-talkies as a sort of an analogy here going forward, because if you grew up playing with those walkie-talkies, a lot of what you learned with them, you'll find it's the same thing when it comes to Wi-Fi. So generally, when we're talking radio waves, as frequency goes up, the easier it is to cram more data onto it. But also as frequency goes up, the lower the range. So for those of you that are old like me and remember cordless phones, when those originally came out, those were normally operating in the 900 megahertz spectrum. Sound quality was okay, and you could go really far ways. I remember as a kid, being able to take that phone, walk outside, and walk a couple houses down to talk and play with my friends while still talking on the phone. And then what we saw is a move in the early 90s to 2.4 gigahertz phones. 2.4 gigahertz was the move to there was designed for a couple reasons. One was there wasn't a lot of available bandwidth at 900 megahertz. So if you lived in an apartment complex or a condo building, you could come into a situation where you would have interference from your neighbors. You could hear their calls bleeding into yours because there just wasn't enough bandwidth for each phone to be able to have their own dedicated chunk of spectrum. So 2.4 opened up a lot more spectrum for people. And since 2.4 gigahertz is a lot higher frequency than 900 megahertz, you can fit more data on there. So the sound quality went up. But now you can no longer walk down the street and talk to your friend on those 2.4 gigahertz phones. And then later in the mid-90s, they came out with 5 gigahertz for the exact same reason. 5 gigahertz opens up even more spectrum, so you've got more dedicated space for each phone, which is a real big plus if you're in a crowded environment like an apartment building. Gave you that much better sound quality. They were able to offer extra encryption on top of that. But again, your range continued to decrease. So you went from being able to walk to your friend's house and maintain a call to maybe you could walk out to the yard, the edges of your yard with 2.4 to, well, with 5 gigahertz, maybe if you have a bigger house, maybe some parts of your house you couldn't get coverage in at all. Same thing with Wi-Fi, same spectrums being used as was used on cordless phones. Those are the exact same frequencies. So when we're talking about radio waves, generally you'll see on data sheets and tech sheets, stuff like that, power being measured is dBm, decibel milliwatts. On consumer grade equipment, you'll often see it being advertised as milliwatts. It's a 200 milliwatt, router or whatever. So we've got a little chart here showing you the differences here between, what 10 dBm translates to in milliwatts. So when we're talking dBm, for every 3 dBm you increase the output power, it's doubling the milliwatt power. So you can see here going from 20 dBm gets you 100 milliwatts, 23 gets you 200 milliwatts, and then jumping up to 30 takes you all the way up to a full watt of power. The reason why we like to use dBm when it comes to business class products and why you tend to see it used more often there rather than milliwatts is 2 reasons. The first one is antenna gain is measured as dBi, loss is measured as dBi. So you can take the dBm coming out of the chip, add in the amplifier, subtract connector loss, add the antenna gain, and really easily add those together to find out what your actual radiated output power is coming out of that antenna. The other reason for it is because Wi-Fi drops off really quick. So just from being able to visualize how much performance gain you're going to get, if you looked at milliwatts, you'd say, hey, going from 20 to 23, I'm going to double my range, right? We've doubled the power, so you've doubled your range. And the reality is, no, it doesn't work like that. It's much closer to this type of performance increase. Just a small performance increase generally when it comes to range. Some other terms that you'll see thrown out there and things that people tend to overlook a little bit. The big one here is signal to noise ratio. This is probably the #1 cause of great or poor performance. So it's talking about the strength of the signal versus the level of noise on that same frequency. So an analogy here would be just having a conversation with somebody, right? If you're in a conference room and it's just you and your friend in that meeting room, you can talk at a normal voice level. You hear each other because there's not a lot of noise around there, right? But if you go out and have a conversation, say inside a restaurant at lunch, you may need to raise your voice to hear each other because you've got all this other noise coming from the other sounds in the restaurant, other tables, people talking, the sounds of dishes being clanked together, things like that. And then if you go out to a nightclub and try to have that same conversation, you've got to get really close to each other and start shouting in each other's ears. Why? Because the noise has gone up. So you have to boost up your signal. So it's the same thing with Wi-Fi. The better the signal to noise ratio, the better the performance is going to be. And then another term you'll see used a lot is attenuation. That just basically means how much the signal is degrading. So the signal will degrade more traveling through physical objects than it does traveling through just open air. So if you go, well, Sean, you know, I want to know how far this signal is going to go. This right here, this is the formula to calculate how far your signal is going to go, basically. And this is assuming just open air. So you can see it's not an easy formula here. You know, 20 log 10 over distance plus 20 log 10 over times frequency plus 92.45. So if you're doing outdoor links, you kind of need to know this stuff. Luckily, if you go online, there are free websites and there are paid tools you can get if you're trying to do long links where you can calculate how far you can really go, and they can also add in things like walls and stuff like that. But generally, when we're talking about distance, you know, and coverage, it's not as easy to calculate as people think. Yeah, we just want to talk here a little bit about attenuation, so things that cause loss. So this will show here, you know, just traveling the Wi-Fi signal go through a window gives you up to 3 dB of loss, right? So it halves your signal strength. Tinted windows, we got some metal on there, that's going to block more, and more than double how much is being lost. And then walls, depending on the wall construction, eats up a lot of your signal just going through there. So the other thing to talk about here is when we're talking about our Wi-Fi range is that Wi-Fi is two-way communication. You know, it's not just one person shouting at the other. And that's something that people tend to get a little bit confused about. So what happens is you know, your traditional access point these days, you know, most business class access points are somewhere in the, you know, 200 milliwatt to a 1 watt output power. But most of your mobile devices, such as your iPhone, are in the 8 to 25 milliwatt output power. So there's a huge discrepancy on how far those signals can go, or as an analogy here, how loudly each device can shout. So even if you're just doing something like streaming Netflix, you go, I'm streaming Netflix, Sean, that's all download, you know, it doesn't matter, you know, how loud I am because the AP is getting the signal to me just fine. But when it comes to TCP/IP and other communication tech protocols used on the internet, basically the access point is going to send a little bit of data to the client, and the client needs to reply back, hey, I got that data, send me the next chunk of data. So if the access point can't hear the client device, you're going to have poor performance. So one of these things that people run into a lot and get frustrated with is your phone. You'll look at your phone and your phone will show you've got 3 or 4 bars of signal strength, that your Wi-Fi sucks. And the reason that's happening is because your phone is telling you how strong the signal is from your access point, but it doesn't know, you know, how strong the signal is getting back to the access point, whether the access point can hear it or not. So you'll often run into that situation where your phone shows you've got a strong signal, but your Wi-Fi isn't working. And that's very often the reason why. So now let's talk a little bit here about RF behavior. So again, Wi-Fi are radio waves, and they behave surprisingly like waves, water waves. So if you had a pond or something like that and you've thrown a rock into it, you've seen the ripples come out, those little waves generated by that. It's the same or very similar when it comes to RF behavior. So what happens is waves hit an object, they can get blocked or at least slowed down considerably if they try to penetrate it, something water can't do. But those waves also are going out, you know, in sort of like a circle radiating out from the transmitter. So some waves are going straight, some are going at an angle, they're hitting something and then bouncing off of it and reflecting back. They can hit something and scatter into smaller waves. Depending on how things bounce around, those waves can actually form together and form stronger waves. So there's a lot of stuff that can be going on with those radio waves that you just can't physically see. So the next thing I want to talk about here is when it comes to Wi-Fi, in terms of radio waves, both sides are using the same frequency, right? So if you're at a 2.4, your AP is operating on channel 11, all the client devices are also operating on channel 11. Now, only one device is able to transmit at the same time. Going back to the old analog cheap walkie-talkie days that we had as kids, right? If you and one of your friends tried to talk at the same time, the person you were trying to talk to would just hear a bunch of noise and wouldn't be able to make out what was being said. It's the same thing with Wi-Fi. If multiple devices transmit at the same time on the same frequency, they're going to interfere with each other, and you're basically going to lose the data that's going to be sent. So traditionally Wi-Fi, up until Wi-Fi 6, Wi-Fi 6 has changed this a bit, but up until Wi-Fi 6, basically it worked like this. There was no coordination of who gets to talk. Instead, what happens is each device listens first to see if it can talk. If it decides no one else is transmitting, it will then decide, okay, I can go ahead and transmit. Then if it listens and it sees somebody else is already transmitting, it uses a random number generator to determine how long to wait before checking again to see if it can transmit. So as you can manage, this is really inefficient as you start adding more and more devices, right? So you're wanting to send data, and maybe you wait, someone else is transmitting, so you wait, but you wait too long before checking again. So you could get more data out there if you didn't have to keep, waiting. So that's one problem. The other problem you run into is you've got more devices out there. Two or more devices will decide they want to transmit something. They will hear, or they will listen and say, oh, no one's transmitting, and then they'll both decide to transmit at the same time, causing interference. So that becomes an issue as you get further and further on, as you add more client devices on there. So this is also something that comes up a lot when we're talking Wi-Fi. People will say, well, how many client devices can how many devices can I have connected to your AP? And if you look at the data sheets, you'll see these really large numbers, right? You'll see 256 or 512 or whatever it happens to be. But in the real world, you'll never get anywhere close to that because of this issue here. You'll get too many devices on there trying to transmit at the same time. And what'll happen is you'll end up with multiple devices transmitting at the same time, degrading performance. So generally, you're going to start running into issues with the way Wi-Fi works and the protocol long before you hit the theoretical maximum that the device it could actually handle. So this is another problem that's kind of related to the last one we were talking about. And this is called a hidden node problem. So what happens is you've got your access point here in the middle of the room. It's nice and powerful, and it's able to send its signal out really far in both directions. You've got two client devices on opposite ends of the room from each other. So these client devices, they can see the AP. The AP can see both of them, but they're too far from each other, so they can't see each other. So when they go and check to see if somebody's transmitting, so this one goes and says, hey, am I safe to transmit anything? It'll listen. It won't hear that this one is transmitting, so it will decide to transmit. And then your AP ends up hearing both of them. And again, packets get garbled, and it ends up having to drop the packets, and you have to end up retransmitting. So that's what we call the hidden node problem. And again, you run into more and more of that as you add more client devices into that wireless network. So the next thing I want to talk about is data rate versus throughput. So I want to start this by saying, the way I'm defining and using these terms isn't the only way to use them, but this seems to be the way that you see it most often, especially if you're doing something like reading Amazon reviews. So one of the problems we'll run into, right, is you'll say, hey, this is a N300 access point. It has a 300 megabit data rate. People will take the access point home, plug it in, and they'll go to speedtest.net, and they'll go, hey, I'm only getting 109 megabits throughput. You lied to me about what your speed is. And the answer is we didn't really lie. It's just it's not clear to people a lot of what's going on. So when we're dealing with networking stuff, even Ethernet, the speeds that are claimed, right, 10, 100, gigabit, whatever, are looking at how much data is sent between both ends of the connecting device. So in the case of Ethernet, it's the data being sent from switch 1 to connected device 1. In the case of Wi-Fi, it's how much data is being sent from, say, your laptop to the access point and back. when it comes to Ethernet, there's not much difference because really Ethernet has almost no overhead. So that amount of data that's being sent is entirely the data that the end user is trying to send. Wi-Fi and power line and things like that aren't these nice, clear, dedicated connections. It's this open radio waves in unlicensed spectrum that anybody can use to do just about anything they want, within FCC regulations. So in order to make that work smoothly and stuff like that, they've added a lot of protocol overhead, error checking, checksums, handshaking, things like that to make sure that the data being sent from point A to point B, when it arrives at point B, is exactly the same as it was at point A. So because of this, there's up to as much as 60% protocol overhead that's going on. So if you're trying to send, download data from speedtest.net, you're sending that data, plus you're sending all the protocol overhead between the actual wireless link to make that wireless link work. So data rate is telling you the physical amount of data that can be sent, or the link rate, whatever you want to call it, but that includes all the protocol overhead. Whereas throughput, as people tend to usually use the term and measure it with something like speedtest.net, is only measuring how much data they're sending from, say, speedtest.net server to the PC, and it's not looking at the other data that gets tacked on top of that by the Wi-Fi protocols to make it work. So that's why you see some huge differences. In general, throughput you should be able to see is at best about 50% of the data rate. And even then it can be a lot less than that, right? Because you've got issues with signal to noise ratio, which might be slowing things down. Distance, signal strength might not be good enough, et cetera, et cetera. That can be causing problems, weakening the signal and slowing things down. So that leads us to the question, how do I increase speed? So I'm going to take a look at increasing speed, not from what you can do in your home, but what do we as the manufacturer, what do we as chipset vendors, what does the technology do to make you get faster speeds? So the three main ways you increase speed, such as when we go from G to N or N to AC, one of the ways we do it is encoding. So encoding here, we have 64-bit QAM, 256-bit QAM, 1024 QAM. So this is the encoding level. So basically how much data, we take the data, how much we can cram onto those 2.4 or 5 gigahertz radio waves. So to fit, well, why didn't we do more QAM to begin with? And the answer is it takes a lot of horsepower, right, to take the data, compress it, put it onto there, receive it, and then decompress it and unencode it, basically. So it's just been a matter of technology having the horsepower to do it and having efficient horsepower so it can be done on mobile devices without killing the battery. So that's why, it's a slow, gradual increase over time. So as you can see here, we went from 64 QAM with 11N to 256-bit QAM and 11AC up to 1000 QAM in Wi-Fi 6. The other thing we can do is increase spatial streams, and I have a slide explaining what spatial streams are coming up here. And the other way we do it is increasing the amount of bandwidth, right? So 11G used 20 megahertz channels. 11N increased that up to 40 megahertz channels. And when 11AC launched, it used 80 megahertz channels, and Wave 2 11AC could use up to 160 megahertz channels. So we'll start from the bottom there. We'll start with talking about channels a little bit. So when it comes to the 2.4 gigahertz spectrum here in North America, you've got 11 channels, right? When you go in there into your AP settings, you'll have 11 channels to choose from. The problem we run into here is we're using 20 megahertz channels, and the total available spectrum that can be used in 2.4 is around 60 megahertz. So you've actually only got 3 channels you can use that are not going to cause interference with each other. So that's something that people tend to overlook, especially beginners in the Wi-Fi space. So when you're planning things out, you've only really got 3 channels to use from, assuming you're using 20 megahertz channels. But as mentioned before, 11N added the ability to use 40 megahertz channels. So you've doubled the amount of bandwidth available. So that doubles how much data you can pump out. But the problem you run into, again, is there's only around 60 megahertz available for use here in the US. So that 40 megahertz channel, you've only got one of those that you can use. As soon as you add a second one, you've got a lot of overlap and you've got a lot of interference. So 40 megahertz works great if you've got a nice large home, you've got some space from your neighbors. Doesn't work so well if you're in an apartment building or condo or an office. So often what happens is you end up dropping back to 20 megahertz channels. Real world. So similar thing on 5 gigahertz. You might remember talking about 5 gigahertz opens up a lot more spectrum for us. So now instead of having 3 non-overlapping channels here, we've got over 20 non-overlapping channels in theory that you can choose from. But you will notice here in the middle, there's this big chunk of stuff here that says DFS channels. So why did we choose to highlight those and call that out? So basically DFS channels, you know, when the FCC decided to open up 5 gigahertz for use for Wi-Fi and cordless phones and things like that, part of the problem was a big chunk of this 5 gigahertz spectrum is already being used, particularly by weather radar and military usage. Airport radar as well. So the FCC said, hey, you know what, you can use these channels if they're not in use where you are, but you specifically, in order to use these channels, the device has to be able to listen, make sure there's not some sort of radar or other government use of this frequency at that time before you can use it. And if it suddenly it is put into use, you have to stop broadcasting on that channel. So it could cause some issues as far as, you know, usability goes, right? If you happen to, you know, periodically get some radar usage, suddenly all your users get kicked off. I want to say it's 30 seconds. I could be wrong on this, but before you start broadcasting on another DFS channel, you have to wait, I think it's 30 seconds to make sure that DFS channel is not in use. So users will get kicked off for a while before being allowed to reconnect on the new channel. The other problem you run into with these DFS channels is to get DFS certified, it can take up to 6 months on top of the normal FCC certification. So for instance, in the case of a lot of our Zyxel equipment, when we initially ship those business APs, such as our current Wi-Fi 6 AP, it does not support DFS channels today. And that's because we're waiting to get it certified. So we will be releasing new firmware next month that finally unlocks those for people. But when it comes to consumer grade equipment, a lot of products never even bother with that, right? End users don't want to update firmware, things like that. So a lot of consumer equipment just doesn't support those DFS channels. So if you're even in a business environment where people are bringing their own devices from home, that is often an issue. It is something that we get calls about at our tech support all the time. Hey guys, I put in your equipment and it's working great except for Bob. Bob can't connect. What's wrong? We connected with our old equipment and then we log in and we see, oh, you're using DFS channels. Why don't you try switching to a non-DFS channel, and suddenly Bob's computer is just fine. It's because Bob's computer didn't support DFS channels. So again, going back to 20 megahertz channels here, we went from over 20, right? If we subtract those DFS, because we don't want to deal with that, you've now reduced yourselves down to 9 non-overlapping 20 megahertz channels that you can use. But again, we were talking before, the way we increase speed is by increasing the bandwidth we're using. So if we increase those channels to 40 megahertz channels, now you're down to just 4 that you can use without causing interference. So again, not a big deal if you're in home, but a big deal for condos, apartments, and a lot of business complexes where you have multiple businesses operating out of the same building that border each other. But we want more speed, right? So 11AC added the ability to do 80 megahertz channels. So now you're down to just 2 that can be used before they start causing interference with each other. And if we go up to those 160 megahertz channels, we absolutely have to use DFS. And even with DFS, there's only 2 channels that can be used before you start causing interference. So something to keep in mind when it comes to interference and why you might be having issues out there. So now we'll talk a little bit about spatial streams. So back in the old days of 11A, B, G, you might remember we talked about before, you know, how the signals sort of radiate out as a circle, similar to a wave in a pond when you throw a rock into it, and it'll go out in different directions and it'll reflect off of stuff. So you can see here, you know, this signal's going out, it's hitting that wall, reflecting in, it's hitting this other wall at a different distance. So what ends up happening is it's similar to an echo, right? You go into a room, you shout out, and then you hear the echo, and you'll hear different, delays based on how many different surfaces in the room it's bouncing off of, and because those surfaces are different distances from you, they come back slightly spaced apart, creating what's called an echo. So with A, B, and G, this was the bane of Wi-Fi, this horrible multipath problem, because it's essentially creating echoes of the data, making it hard to understand, recognize the signal it's supposed to hear from all these other signals coming in. So this was horrible. So some engineers that are way smarter than me, some of whom worked at our old Zyxel chipset spinoff, which was eventually purchased by Atheros, came up with technology to turn this multipath problem into a multipath benefit. So we know that this signal goes out, we know it's reflecting off of things, and we know that you're hearing the same signal coming in like an echo, slightly spaced out. So they said, you know what, we can take advantage of that. We can create an access point with multiple antennas, and we will simultaneously send different data out of each antenna. And because those antennas are spaced slightly apart and some other funky stuff they do in the back end, we'll be able to bounce those off of objects in the room. They'll come into the other side slightly set apart, and we've now got the technology to basically listen to each echo independently and then combine them back together. So this is something you started to see in 11N, right? We had N150, N300, N450, and that's how they were getting to those speeds, is they were taking this and sending different paths and sending different data over each path. And then at the end, the person listening is able to combine those together. So it allows us to use the same frequency simultaneously to send different data simultaneously. So that's MIMO, or MIMO as Jacob likes to say. So each stream has a different amount of data. So again, going to 11N, each spatial stream can carry up to 150 megabits of data. So if you had a 2x2 device, or if you had a device that advertised itself as N300, that told you it supported 250 megabit spatial streams. If you had a device that called itself N450, you knew it could support 3 spatial streams, each supporting 150 megabits per second. Now with 11AC Wave 2, they added something new called MIMO. So in the past, MIMO was used, right, to send different data simultaneously to one device where it was then added back together. So with Wave 2, we gave access points the ability to send data to multiple client devices simultaneously. So instead of sending 2 streams of 150 to the same device, we're now sending 1 stream of 150 to one device and a different stream of 150 megabits to another device. So the overall aggregated throughput is 300 megabits still, but it's spread between multiple devices. So giving you more efficiency. And this is really big because your access points are likely to be 3x3 or 4x4, or in some cases even 8x8, where a lot of your cheap client devices, or even not so cheap client devices, were only 1x1 or 2x2. So you would have spatial streams basically going unused. So MIMO allowed you to use those spatial streams to send data to multiple clients. So you'll see this a lot again on business class data sheets. On consumer data sheets, you'll see, N300, AC 2600, blah, blah, blah. Generally on business class products, you'll instead see the speeds defined as how many spatial streams these support. So 2x2, 3x3. So the first number is telling you how many spatial streams you can transmit. The second number is telling you how many spatial streams you can receive. In general, on access points, the numbers will always be the same. If the first number is 2, the second number is 2. However, on client devices, you will often see 1x2 or 2x1 because the device is able to, say, receive 2 spatial streams, but it's only capable of sending out 1 spatial stream. So that becomes important on the client side of things. The other thing you will see, particularly on some Cisco equipment, is you will see a colon. So you'll see 4x4 colon 3. So based on what I just said, you'd say, well, that supports 4 spatial streams. But I don't know what that colon's for. What's that number after the colon? And the answer is That's actually how many spatial streams it supports. So they're saying, hey, we've got 4 antennas that can be used to transmit, 4 antennas that can be used to receive, but we're only actually going to use 3 of those at one time. So this was kind of their way. They don't have smart antenna technology. And I'll talk a little bit about smart antenna later. But this was kind of their way of doing it. So instead of having a smart antenna, you let the AP decide, you know, which 3 out of those 4 antennas to use at any one time. In theory, one of those antennas could have a little bit better signal reception or whatever than the other ones. Real world, though, it didn't really make a lot of difference. So putting it all together, we've got a nice little chart there for you. Here's your spatial streams. Here's your modulation type, or your encoding. And here's your column showing how much radio bandwidth you're using, whether you're using 20 megahertz bands, 40 megahertz bands. So you can mix and match those to try to figure out what the maximum speed is. So generally when we're talking data rates, when you see advertised speeds out there, they are taking the best case scenario, right? So if you were to get a 1x1 11 AC product, it would probably be advertised as AC 900, taking this 866 and rounding it up to 900. So that's assuming 160 megahertz bandwidth being used, 256 QAM, 1 spatial stream. So you're always going to have the 1 spatial stream, but realistically, unless the signal strength is strong, or I should rephrase that, if the signal strength isn't that strong, it will drop back to 64 or 16 QAM. So your real world speed may be lowered to 650 or 390. I also mentioned before, you know, there's limited amount of space. So if you're in an apartment or an office, you might not be able to use 160 megahertz channels. You might only be able to use 40 megahertz channels. So suddenly we go from 866, we're only using a 40 megahertz channel. So now we're down to 200 megabit speed, but our signal strength isn't that strong. So we've dropped to 64 QAM. So the maximum data rate's only 150 megabits per second. So a little bit confusing, but I hope that sort of makes sense on how to combine those two together and how it affects the type of performance you can expect to see out in the real world. So I already hit on this before. So, you know, when it comes to how many devices can I get on your access point, as a general rule, it doesn't matter whose access point you are using. Doesn't matter if it's a cheap one or expensive one, if it's a $2,000 Cisco, if it's, you know, a cheap TP-Link $60 one. Generally, the number of users is going to be defined by the types of devices, the types of traffic, and just the Wi-Fi protocol itself. That's going to hit your cap long before you get to whatever number is on your data sheet. So I'm using this as an theoretical example here. We're basically taking an access point out there. We're simulating clients. Each client is trying to view a 3 megabit video stream called a YouTube stream, 3 megabit per second encoding. And the only thing we are changing here is we are changing the type of device for this scenario. And the difference between each device is only how many spatial streams each device supports. So if we go here with a laptop that has a 3x3 in there, and we're connecting to a 3x3 access point, you can have 34 devices connected and able to maintain that 3 megabit stream with no issues. As soon as you add the 35th on there, you're going to start running into issues with buffering and things like that. So we remove one of those spatial streams. Now we can only fit 21 devices onto that access point and be able to maintain a 3 megabit stream for each, right? So our capacity here has just dropped from 100 megabits aggregated throughput down to 65. And we've lowered the number of devices simply because one of those spatial streams isn't being used. Drop another spatial stream down here, and now you're down to just 10 devices on that same access point watching the exact stream YouTube stream that you can fit on there. So that's just looking at spatial streams. Obviously, you start throwing in signal strength issues, encoding issues, things like that, and it becomes messy. But I just wanted to show here and highlight here what a big difference just one thing spatial streams are going to make to the number of devices that can be connected in using the connection without issues. So we've talked a lot today about interference, right? So the proper term here is co-channel interference. So it's other devices broadcasting on the same channel. It could be the hidden node problem we talked about earlier. It could be just the issues with two devices deciding to transmit at the same time. It could be interference from your neighbor who is using the same channel you are. It can be other APs in your office because you've only got so many channels to choose from. So traditionally, the way you've dealt with co-channel interference is you would get a floor plan and you would plot out where each AP goes, and then you would try to pick and choose channels, right, to make sure you had no APs at least directly next to each other using the same channel. But obviously that gets really hard to do if you're trying to use bigger chunks. You're trying to use 40 megahertz or 80 megahertz channels. And the other thing we talked about before is there's obviously this huge power discrepancy between the AP and the client device. And most of the time people operate their APs at full power. So even though the client devices aren't having a strong connection, you can be causing interference hundreds and hundreds of feet away to another AP on that same channel. So the way we kind of dealt with that historically was we would turn down the power, right? So you'd get less interference, the signal strength would be restricted, and that was how you did it. You carefully plotted out your channels, and then you would tweak the power of each AP until you got things working good. Obviously, though, the problem is you reduce your output power, you're also worsening your signal to noise ratio. So you may run into issues where, okay, you're not dropping packets due to interference, but your signal to noise ratio is worse, so you're operating at a lower speed in general. So the overall aggregated throughput may be the same. So our solution to this is something called smart antenna. So traditionally, an access point has one fixed antenna pattern. If you're talking about your typical office access point, it's got what we call an umbrella shaped pattern. The AP goes here in the middle, and it's got roughly a circular coverage area of the signal radiating out in different directions from the AP. In the case of a lot of your outdoor stuff, you have directional antennas where you're focusing the beam and focusing it in one direction. So smart antenna instead goes through hundreds upon hundreds of different antenna patterns, and it does this for each individual client. So it will choose the best antenna pattern to use for any particular client based on where that client is in relation to the access point. And in the case of our algorithm, we spend a lot of time focusing also on interference. So we focus the beam pattern to sort of ignore other sources of interference. Now this technology, it just is done on the AP. It doesn't require anything special be done on the client side. So it'll work with any type of client device. And also, unlike some of the other technologies out there, the client device does not have to be static. We will modify the antenna pattern in real time as mobile clients move about. So I do want to show some examples here. So in this case here, we are using our NWA 1302 access point, and we are using a Ubiquiti, their version of it. Very similar form factor, very similar power output, both are 2x2. And we've taken this here. This is a hotel layout, but you could consider this to be similar to an office building where you're covering different areas in the building. And it's just showing here, we've carefully plotted out the different channels to make sure there's nobody on the same channel directly next to each other. In this case, they're spread across two different floors. So this floor is above this floor. And we went ahead and decided to test these and see what happens. So to begin with, we started with just one access point. We had that set up and turned on. We connected our clients to it, and we did some throughput testing. And you know what? Ubiquiti beat us. Not by much, but Ubiquiti outperformed us. You can see here aggregated throughput. It was 406 megabits per second versus 404 on the Zyxel. When it comes to airtime utilization, it's both basically the same. About 67% of the theoretical maximum airtime was used. Now you go, well, why was it only 67? Why wasn't it higher? And the answer is, again, when you have multiple clients, right, there's nobody coordinating who gets to broadcast. So what happens is, they listen if someone else is broadcasting, you wait a random time before it's your turn to try broadcasting. And because of that, it introduces inefficiencies in airtime utilization. There will be gaps where people could be transmitting, but nobody is because they're waiting for the random timer to come up again. So next we went and turned on two APs. Now we've got two APs, not directly next to each other, but two APs operating on the same channel in the same building. And we did aggregated throughput. And look at what happened. Suddenly, our aggregated throughput was 785 megabits per second. Ubiquity's aggregated throughput was 555. And that has to do with the smart antenna. That was the only real difference between us and the Ubiquity, is the fact our AP has smart antenna and is able to go through all of these different antenna patterns that take into account where the client device is. So they're only sending signal in the direction of the client device so they don't interfere with other APs. And also not listening or amplifying the signals coming in from other directions as well. So because of that, you will notice that not only is our aggregated throughput higher, the distribution of throughput between APs is roughly the same, whereas Ubiquity without the smart antenna, one AP is getting almost double the throughput of the other AP. And you can see here when you look down here at channel efficiency, Ubiquity is maxed out at 95% of the available airtime. We're actually able to use 131%, so more than the actual theoretical maximum we're able to hit, because the smart antenna is allowing us and allowing the client devices to operate simultaneously without interfering with each other. So same thing, now we've added a third AP. Again, they're not next to each other, they're spaced out several rooms apart. But like I said, it's that power mismatch, so that signal can actually go quite far and can cause interference. So we see the same thing here. Aggregated throughput is over 900 megabits per second. Ubiquity is still stuck here at under 600 megabits per second. And again, our APs, the throughput is pretty evenly distributed between AP, where Ubiquity, it is not evenly distributed. And the same thing here, channel efficiency, we go up to 155%. Ubiquity actually dropped to 91%. So I'm not trying to rag on Ubiquity specifically here. I'm just talking about the difference between what smart antenna does versus non-smart antenna in a real world environment where you will be having interference. So some other things to talk about here is, again, we talked about before, most APs that don't have smart antenna have this sort of circular antenna pattern that's optimized for mounting the AP on the ceiling in the center of a room and radiating out in a nice round umbrella pattern. But a lot of times, for whatever reason, you can't mount your APs on the ceiling. You have to end up mounting them on a wall. So you can absolutely do that. It absolutely works, but it's not optimal for the situation. You end up sending a bunch of the signal up into the ceiling or down into the floor. If you're in a multi-floor structure, you're going to be causing interference for those APs that are upstairs or downstairs from you. And the signal's not really going out as far over the floor as it really should. So it's not optimal. Now we do have an access point, or a couple different access points. We have dual optimized antenna, where we've actually got two sets of antenna in the device, one for the ceiling, one for wall mount, and you can switch between which antenna pattern to use based on where you've installed it. So that is one way to deal with that other than smart antenna. Smart antenna also solves that problem. So just general rules here when it comes to mounting your AP. You want to try to mount it centrally in the room versus where your users are at. And you want to mount it as high as possible within reason. So you can see here, we've put it here on the drop ceiling. And you can see it allows the signal to go directly from the client device up to the AP with minimal amount of obstructions in the way, where if you mounted it down lower someplace, more of that signal would have to pass through people, cubicle walls, what have you, to get to the AP. So by mounting it up high, you give a clear line of sight between most of the client devices and where the AP is, so there's less attenuation of the signal. And I say within reason here, because if you're in a warehouse with 40-foot ceilings, that's probably too high, and you want to mount it down lower. So a lot of times you mount this to the drop ceiling, but we get this complaint all of the time from our partners, which is, hey, they won't let me mount it to the drop ceiling. Maybe there's some local code that doesn't allow it. Maybe the business owner, doesn't want you drilling a hole through the drop ceiling to run the Ethernet cable out, et cetera, et cetera. And you know what? The easy way to deal with that is to just rest the AP on the other side of the drop ceiling, provided code allows you to do it. All of our APs are plenum rated, so they can be mounted above a drop ceiling in the plenum space. The drop ceiling itself, those acoustic tiles, they don't really do much to attenuate the signal. So oftentimes that's the best way to do it. You just simply lay them. The graphic there is upside down as far as how the AP is, but same way you would mount them on the ceiling, same bottom side being the bottom side, just rest it on top of the drop ceiling, and that tends to work really well. And oftentimes it works much better than mounting them onto the physical ceiling above the drop ceiling, because often those physical ceilings have conduit, water pipes, AC vents, all sorts of nasty metal stuff also running along those ceilings, which will reflect or degrade the signal. So just resting it on the top of the drop ceiling works really well for a lot of people. So when we talk about hotels, the traditional way of doing a hotel was what we call umbrella coverage. You'd put an AP in the hallway, and that AP would cover, depending on what the walls are made out of, depending on the floor layout, would cover anywhere from 4 to 16 rooms. It worked pretty decently back in the old days. And when I say old days, it's because what's happened is how people are using Wi-Fi has changed dramatically in the last 10, 15 years. It used to be, you had one device that you connected to the Wi-Fi. You had some business dude in there, he'd launch his laptop, connect to the Wi-Fi, download and reply to emails all night. Well, now obviously that's not the case. When I travel personally, I've got my laptop for work. I've got my phone, which I'll want to put on Wi-Fi because I don't have an unlimited plan because I'm cheap. And I also have a tablet that I use for browsing the web in bed and playing games and stuff like that. So I'll have at least 3 devices that I want to connect to the Wi-Fi, and that's just me. Throw my wife in there. She's got at least 2 devices she's going to want to connect, throw some kids in there, et cetera, et cetera. So we've now got more devices trying to connect to those access points. A lot of those devices, like your cheap Amazon tablets, some of your cheaper cell phones, don't have a lot of signal strength. So while the laptop may have no problem making a connection, your phone or your tablet may have a problem getting the signal back out to the access point out in the hall. And then on top of that, people are using the Wi-Fi to make calls, to stream video, et cetera, et cetera. So that's a lot more bandwidth intensive than it used to be when you were just checking emails. So because of that, the trend in the industry, starting around the mid-tier hotels and up, has been to move to 1 AP per room or 1 AP per every other room. So like in the slides before where I was talking about smart antenna, I was specifically comparing our and Ubiquity's in-room hotel access points. They're a little bit lower power, they've got pass-through, they're specifically designed for this type of scenario. And this is where things are trending. So if you're putting APs in the room, there's some things to keep in mind. One of them is guests are going to steal those APs. So you want to make sure you've got some sort of locking mounting bracket that keeps them from easily being stolen, or at least is not obvious how you would release the device. So that's something important. It's also important to think about turning off the LEDs on the access point. There's obviously, if you're trying to sleep, you don't want a bright green flashing light shining down on you. I have been in a hotel room in San Diego that had an AP in the room, and it was bright as the sun, or at least it felt like that at 6 a.m. when it was lighting up the room for me. So you want to make sure your APs can turn off the rooms, or turn off the LEDs. When it comes to the public areas, you want to plan for each physical area. So you plan the lobby separate from, you'd plan the convention center separate from the cafe, separate from the hotel pool, things like that. So plot them out separately. Generally, you would do load balancing for the individual area. Clients steering the same, right? You don't want to be load balancing between the lobby and somebody up on the 20th floor. So you'd have those each VLANed out into their own individual segments, even if you're still using the same captive portal for all. Smart antenna makes a huge difference, especially in areas where you've got a lot of users, such as conference rooms, things like that. For schools, it varies a bit because it depends on how smart the school is. Some schools, only certain rooms have a lot of users connecting to Wi-Fi. Some schools, every student has a Chromebook or a iPad and that is connected to the Wi-Fi from the second they sit down in that room till they leave. So that's things you need to know. Is the teacher streaming video to each individual device? We run into that. Sometimes the devices are just there to upload homework and take tests. In some places, the teacher is constantly streaming video or share screening their device onto those devices. So you need to know, okay, how many students are going to be in the room? Do they each have a Wi-Fi device? Is it just for test taking, or are you streaming video? Because obviously video is going to require a lot more bandwidth. So those are the types of questions to ask to try to figure things out. In general, the teacher and the student should be on separate networks, right? You don't want the kids accessing the teacher's resources. So you'd want to VLAN them off, put them on different SSIDs, and only allow sharing through whichever apps need to be shared across those VLANs. Generally, for class sizes, 20 or more, we recommend 2 APs per classroom. If you're using our APs, if you're using our controller or you're using our Nebula Cloud, we have a special load balancing algorithm specifically designed for classrooms where you might have 20 or 40 students all simultaneously coming online. And if you've got 30 or more students, I highly recommend going to Smart Antenna Products. It is worth the extra cost. So I want to talk a little bit here about 802.11ax, aka Wi-Fi 6. We do have another webinar where we just talk about our Wi-Fi 6 AP and go into a little bit more in depth on this. So I'm just going to hit the main things here. So basically, Wi-Fi 6 is designed to work on all frequencies. 11AC only worked on 5 gigahertz frequencies. So if you had a dual band 11AC product, it was still operating on 11N on the 2.4 radio. So with Wi-Fi 6, all of these improvements that Wi-Fi 6 gets work on both the 2.4 and the 5 gigahertz radio. And in the future here, it looks like maybe the end of this year on the 6 gigahertz frequencies as well, as those are being opened up by the FCC. Wi-Fi 6 really starts over from scratch. They've made a ton of changes to fix a lot of the shortcomings that have plagued 802.11 Wi-Fi since the original 802.11 spec. So we've talked about before increasing the QAM. We've added OFDMA. We've allowed uplink MIMO, so multiple clients can transmit data to the access point simultaneously. Spatial frequency reuse, all these other things. It's going to make a huge difference as far as throughput goes, especially in a high density environment. So in an environment where you've got a lot of APs within a small area, there's all sorts of technologies in there that help prevent them from interfering with each other. If you've got a lot of client devices, there's new technologies where basically the AP coordinates who gets to broadcast when. So instead of having like 65% efficiency, like we were talking about before on the ubiquity slide, we can get a lot closer to 100% efficiency with Wi-Fi 6 in theory. What else do we want to say here briefly about Wi-Fi 6? To get all the benefits of Wi-Fi 6, you do need all your client devices to be Wi-Fi 6. And just like with any other Wi-Fi technology, the client devices are lagging behind the access points, right? Because the access points, you know, we can brute force that. We can just shove a ton of power into the AP to power all of this stuff. It's a lot harder to streamline these and make them energy efficient to operate in client devices. So even stuff like the current iPhone, which does claim to support Wi-Fi 6, it doesn't support all of the Wi-Fi 6 features currently. So it's still going to be a few years down the road before you're seeing the maximum potential of Wi-Fi 6. Some interesting fun things here is while the Wi-Fi Alliance is certifying Wi-Fi 6 devices, they started doing that in October of 2019. And you even had some vendors shipping product all the way back in 2018 claiming it to be Wi-Fi 6. The actual Wi-Fi 6 working group is still working on the standard, and they're not expected to approve it until September this year, with final approval being November 2020. So the question is, well, if that's the case, how can we be selling Wi-Fi 6 products now? And the answer is, depending on when those Wi-Fi 6 products came out, you can or can't do it. So basically, there's two major chipset vendors out there when it comes to Wi-Fi 6 chipsets, Broadcom and Qualcomm. And while I've got the slide here just talking about Qualcomm, the Broadcom, if I had a Broadcom slide, it would be almost exactly identical to this. So what has happened is some of these early chips so-called Wi-Fi 6 chips support some of the feature set of Wi-Fi 6, but not all of it. And in most of these cases, the parts that aren't supported are the really important bits that make Wi-Fi 6 different. So these first generation or first 1-2 generations of Wi-Fi 6 chipset are missing some very key features. But they allow companies to go out and say, hey, it's Wi-Fi 6, and we just don't support some of these features. So basically, you want something with a Gen 2 chipset to be able to support all of the features. So by the time the Gen 2 chips came out, so they started shipping to guys like us back in August last year. All of those chips, the Wi-Fi official draft spec for 802.11ax is far enough along that any changes made between then and when the final version is finally signed and finalized this winter, we can tweak and support any changes that are made via software. But so there'll be firmware updates to fully enable those features and to make them fully compatible with the spec. Unfortunately, the Gen 1 and Gen 1.1 and Gen 1.2 chips are never going to be able to get those features. The hardware just doesn't have what's going to be required to support that. So just about anything that you buy that's Wi-Fi 6 today is not supporting all of the features today. Anything using a Gen 2 chipset should be upgradable to support everything that's going to be in there eventually. So something to keep in mind, you're going to go, well, Sean, how do I know if I'm getting a Gen 1 or Gen 2? And unfortunately, nobody puts that on their data sheet. People selling Gen 1 products aren't going to advertise the fact that it's only Gen 1. So you can try reading the data sheets to see which features are missing. But as a general rule of thumb, if the product started shipping before, say, this last fall, September 2019, it's pretty much guaranteed to be a Gen 1 chipset. Most stuff that's launched since then is going to be Gen 2, but on the lower end of things, you may still find guys using the Gen 1 chips because they're cheaper and just leaving out those features. So from a Zyxel's perspective, everything we're shipping that's Wi-Fi 6 is Gen 2. Everything we're shipping should be software upgradable to the full Wi-Fi 6 feature set, if not at launch, soon. So guys, that is it for today's webinar. I appreciate you joining me. I know it's a long webinar. I know it's kind of technical at times, and I'm not always necessarily the best guy at explaining those things, but I hope you found it beneficial. If you have any questions, send them in right now with the Q&A box, and I will try to answer those for you. Some other things I want to highlight here. We do have a user forum, forum.zyxel.com, and unlike a lot of other vendors' user forums, it's not just user on user support. Our teams in Taiwan, specifically our R&D and engineering teams, do keep an eye on that forum, and they do often wade in to answer questions. But it's a great way if you're running into some little niggly issue. It's a great way that doesn't need to be solved right away. It's a great way to let our team in Taiwan know what's going on. It's also beneficial because other users can join in and provide some corroborating evidence if needed to help them try to troubleshoot what the cause of the problem is. And then my email is right there on the screen for you. It's seanr@zyxel.com. Feel free to reach out to me offline with any questions. I specifically handle our wireless products, our general Nebula Cloud, and most of our consumer products, and a few of our business switches, the lower end business switches. So you can reach out to me about those. You can also just give me general feedback. How can we make these webinars better? How do we make these more useful for you and your team? And you can also give us some suggestions as to what you'd like to see us cover. Many of the webinars we are doing today came about because people like you emailed us and said, hey, it'd be really great if you did a presentation about this. So that lets us know what to do and how to make it for you guys. And I am not seeing any questions come in, which is really odd for this webinar. So I'm going to go ahead and end today's webinar. If you're typing something up now, highlight it, copy it, and just email it to me. Again, my email is seanr@zyxel.com. I'll reply to you offline. And if for some reason I don't reply to you within 24 hours, send it again. I'm not ignoring you. Chances are it got caught in one of our 3 different spam filters we use here at the office. So hopefully the next one will either come in, and I do check those, but there's so much garbage in there, occasionally I miss it. So if I don't get back to you within 24 hours, just resend it to me, and chances are I'll catch it the second time. All right, thanks guys, appreciate you joining us.